Hello and thank you for watching this video. In this video I want to introduce the Duhem-Quine Thesis, which is both historically a very hot topic in philosophy of science, as well as building very closely on the video I made recently on the problem of underdetermination, so feel free to check that out if you are interested. In any case, in that video I referenced the thesis in reference to the holism of theories, i.e. the notion that one is not testing individual hypotheses in isolation, but rather a bundle of theories due to various background assumptions, where in relation to the problem of underdetermination, the Duhem-Quine thesis forms one localized subset of this problem. Localized here in the sense that while underdetermination posits that any empirical evidence can always be accounted by a host of mutually incompatible theories, the Duhem-Quine thesis in turn focuses on individual tests such as hypotheses and theories. But let's organize the video as follows. We will first look at the individual actors as well as the history of the problem. Secondly, we will look at the challenges this poses to science, where we will learn that the problem may also potentially be extended to logic and mathematics, as well as look at an example in the end there. We will thirdly look at some responses to the problem before moving to the last part of the video, where we will summarize the implications of this problem for the scientific method, or as I like to call it, scientific methods, as there are many different methods in science. I'm of course not the first to point this out, as scientific methods is also used quite frequently. In any case, so with that out of the way, let's introduce our two players in the field. Duhem refers to Pierre Duhem, who was a French physicist who was obviously not just concerned with the development of physics research, but also had broader interests in terms of the methodology of scientific testing, as well as theory development. He therefore first introduced what later became known as the Duhem-Quine Thesis in 1906, under the publication of his book, The Aim and Structure of Physical Theory, where he argued that each time we are conducting a physics experiment, we are not just testing one theory, but rather, in fact, a whole group of theories together. To quote, "There exists at every historical moment the heritage of previous history, a body of trusted theories which guarantees the experimental physicist the possibility of making observations without having to doubt every concept used. Thus, science may progress constantly, increasing the theories it trusts, the background knowledge in modern terms. It makes statements which, from the logical point of view, are unavoidably theoretical. They are theoretical at the moment they are proposed, but they become increasingly more experimental as they are provided with increasingly more guarantees of their validity." This idea of a nested set of theories later became fundamental for Quine as a form of thinking about a network set of theories or knowledge, which became an integral part of the former's philosophy. On the other hand, if we really want to get into the weeds of philosophy, if you read Duhem's book, it's clear that the book has a different scope and focus than Quine had. For instance, Duhem favors a form of instrumentalist view, which is not shared by Quine, but we can nonetheless link the two people together under a shared umbrella regarding scientific holism. This last point regarding the differences between the two is also brought up in the article The Duhem Thesis and the Quine Thesis by Donald Gillies, in case you're interested in reading more about the differences between the two. I'll try to link that in the description as well. In any case, let's move on to Willard Quine, who can be described as one of the most influential and premier figures of philosophy of the 20th century, who started out his career working in logic especially. In fact, he wrote some very regular textbooks in the subject before moving on to discuss more broader issues in science and other fields of philosophy as he matured. I would say that he is someone who I like to think of as carrying the torch of empiricism in many ways, but in a way which gave a modern updating of the position, as well as going against the grain of logical positivism which he rejected at the time. You can read his reasons for this, amongst others, in his famous paper, The Dogmas of Empiricism. It was also in this paper where he introduced the problem Duhem had observed much earlier, which led to the Duhem-Quine Thesis becoming mainstream within philosophy of science. He is also someone partial to a science of metaphysics, criticizing an overtly a priori approach to metaphysics, where he viewed metaphysics as being very much continuous with that of science. Also, for those interested, I have a video on scientific metaphysics as well, so feel free to check that out. Furthermore, he also took a naturalized stance in terms of adopting a naturalized epistemology, which meant that the logical entailments for how we come to know things, facts about the world, stems from processes understood in terms of empirical science, where natural candidate fields in this matter to consult would be psychology, neuroscience, and sociology, for example. As a matter of historical interest, although he tried to get as close to empirical evaluation as he could on most issues, he interestingly did adopt metaphysical acceptance of abstract objects, as he was ultimately not convinced by nominalism, the view that only particulars exist, which denies the category of universal entities as abstract objects. This, in fact, again brings us back to the Duhem-Quine Thesis, as Quine held the position that you cannot neatly excise abstract objects, as found in mathematics, from empirical science, without tearing the whole network of beliefs that make up the package of beliefs that we test under hypothesis testing, which certainly is an argument inspired from a holism in science. Thus, to end off this section, we give a more formal definition of the thesis, before we will in the next section move on to look at some of the entailments of the view. So again, to reinforce our learning, the Duhem-Quine Thesis can be viewed as the view in philosophy, which claims that from the observation that we have an inability to test hypotheses in isolation, then this will leave us underdetermined in our response to a failed prediction, or alternatively to some other piece of disconfirming evidence. Moving on to how this thesis impacted the whole domain of science, and in particular our way of thinking about scientific experiments, this can be neatly illustrated in regards to Karl Popper, who introduced very firmly the idea of falsification of scientific theories. For Popper then, science relies not on induction as Hume had earlier postulated, but instead relies entirely on deductive falsification. We thus here imagine a scenario where instead of collecting samples of 1,000 numbers of white swans and inferring whiteness of swans, Popper here instead argues that you cannot ever use an arbitrary large amount of supporting observations to verify a theory, but what you can do is use a single contrary observation that can then logically and conclusively refute it, giving us deductive falsification. Therefore, in our example, seeing one black swan logically proves immediately the rule that all swans are white must be false. But if we bring in the Duhem-Quine Thesis, then it's clear that we can argue that what a falsification shows is something in fact much weaker, as it only shows that there must be a problem somewhere in the network or package of theories being tested. Another problem for Popper is that it's not clear how he even avoids induction, as every experiment itself relies upon underlying assumed inductions about the success of experimental equipment and methodologies at successfully refuting a theory. Thus, the problem is clearly more complicated than Popper first thought, as holism allows researchers to save their main body or core of their scientific theory, if you will, by instead blaming background assumptions. This has again led some philosophers to go as far as to state that no scientific theory can ever be conclusively refuted, thereby repudiating the core feature of falsifiability as held by Popper. Here I give an excellent quote which summarizes just how much of a nuisance holism in theory testing is for the strict form of falsification, which many have claimed Popper wants us to endorse, to quote, "Our inability to test hypotheses in isolation leaves us underdetermined in our response to a failed prediction or some other piece of disconfirming evidence. That is, because hypotheses have empirical implications, or consequences only when conjoined with other hypotheses and/or background beliefs about the world. A failed prediction or falsified empirical consequence typically leaves open to us the possibility of blaming and abandoning one of these background beliefs and/or auxiliary hypotheses rather than the hypotheses we set out to test in the first place. We can conclude, therefore, that if the Duhem-Quine thesis goes through, then it will certainly be used as it has been used historically to reach conclusions about the limitations of empirical evidence and the rules of scientific methods, as constraining our own acceptance or rejection of scientific theories. However, we don't want to strawman Popper here, so it should be noted that Popper thinks that falsification does not contain a final, absolute, secure foundation, but we will look at responses later in the next section. In any case, Quine also argued that we can extend this problem to logic and mathematics by moving from empirical science, where we make testable observations and potentially modifying our theories, to the strict formalisms in mathematics and logic, where Quine thought that it was possible for new empirical observations to potentially modify the strict basis of both mathematics and logic. In contrast to Duhem, then, these fields are part of a broader network encompassing holism for Quine, where this should be seen as a rather controversial view given the enormous cost of revision in these fields due to their centrality, as well as the fact that it risks making mathematics and logic an empirical basis. After all, we might then ask what is really the distinction between science and mathematics if we adopt this holism under Quine. These remain in any case very big challenges for the view, in my opinion. To look at an example, we will here consider an experiment which incorporates the failed scientific theory of ether, i.e. the theory that space itself was composed of an invisible, weightless, mysterious substance that acted as a medium for all sorts of forces such as gravity, temperature, and electromagnetic waves to travel through. Thus, the Michelson-Morley experiment from the late 19th century attempted to detect the Earth's motion through the hypothesized luminiferous ether. Amongst other, the experiment crucially relied upon an optical interferometer invented by the physicist Michelson. In the experiment, which is an instrument used for measuring precisely beams of light, taking into account variables such as length, surface irregularities, and index of refraction. In any case, using the interferometer in the experiment, we're comparing the optical path lengths for light moving in two mutually perpendicular directions. Michelson made the hypothesis that if the speed of light was constant with respect to the ether through which the Earth itself must move, then it must be the case that motion could be detected by comparing the speed of light in the direction of Earth's motion and the speed of light at right angles to the Earth's motion. However, it turned out that when they performed the experiment, that no differences were found, which led historically to the theory of ether being largely discredited. If we now analyze the experiment in relation to the Duhem-Quine thesis, we would firstly have a whole bunch of conjunctions of assumptions in the experiment, where we now know that some of these are false, such as the ether theory and the classical velocity addition of light, which predicts that a light beam's speed changes depending on how fast the source moves. But we know light always travels at a constant speed for all observers, as Einstein famously put it later. We could now list some of these conjunctions in the experiment, as for example ether theory plus Earth must move through ether plus classical velocity addition, which utilizes simple vector additive properties of light, plus assumptions regarding the accuracy of instrumentation and so forth, which at an index up to n we will represent as h1 and h2 and ... and hn. Now, according to the Duhem-Quine thesis, we would only obtain a negation of the conjuncts, as if we assume the predicted consequence p here fails, that is the consequence that the measured speed of light would change depending on the direction of Earth's orbital motion, producing in effect a noticeable shift in light wave interference patterns when rotated. Or more technically, there was to be a predicted noticeable effect size consequence of rotating the interferometer by 90 degrees that would swap the roles of the light beams and cause a measurable shift in the optical fringe inference pattern. So we will denote P as an expected fringe shift. Hence what we logically have here is H1 conjunction H2 conjunction ... conjunction Hn implies P, not P. Then we obtain the negation of the conjuncts, that is, negate H1 conjunct H2 and so on. However, we should observe here that crucially, this does not tell us specifically which of the hypotheses Hi should in fact be rejected, meaning we are not testing for the ether theory in isolation. This, according to the Duhem-Quine thesis, would leave the door open, so to speak, to instead, given the outcome of the experiment, instead here we could modify the auxiliary hypothesis in order to save the core theory of ether. Therefore, one could interpret the experiment as being compatible with different revisions of the surrounding theoretical network, where crucially we are in trouble here, as the observation itself does not uniquely determine which theoretical commitment must be changed. This gives credence to the historical picture that we observe here, where Michelson and Morley themselves continue to believe in an ether theory, and other physicists, or I should say some other physicists as well, subsequently try to modify ether theory rather than abandon it fully. One could still argue, of course, that the theory of ether was greatly diminished and some people would have still abandoned the theory on the grounds that the experiment showed that the straightforward version of the ether hypothesis was failed according to an important prediction, and retaining the ether now requires additional theoretical machinery. So there is a failure here in terms of requiring additional theoretical machinery. We could, for instance, bring in scientific virtues here, such as scientific simplicity or parsimony, to argue for a diminishing effect to the theory of ether, which would certainly be an option. Notice also here as a side note the importance of logical representation, in that it has the effect of clarifying methodological questions about what we need to test, and this is really a hallmark of the logical empiricism in the 20th century, the fact that we can really utilize logic in terms of representation of scientific ideas, and it can really have an outcome or effect in terms of the methodology itself, which is really a core philosophical view of the logical empiricist school of thinking. But in any case, having briefly discussed the experiment, let's move on to the third section, shall we? We threw Popper rather hard under the bus in the previous section, so we should first look at some of the responses from Popper and others to the extent that the Duhem-Quine thesis poses a problem for his view, and moreover, especially when it comes to his principle of falsification. Remember here that Popper's method itself relies heavily upon hypothesis testing as the main activity, if you will, for scientific research. Now, if we again return to the logical form, which we just introduced in the example before, where we here let T represent a scientific theory, AI denote the different auxiliary hypotheses, then we again arrive at the same situation from before, from the implication T conjunction A1 conjunction ... conjunction AN implies P. From this form we only obtain not P, and then we end up in the same situation as before, where we get the negation of the conjuncts, that is, negation of T and A1 and so forth. Which again tells us that we cannot conclude, as Popper would want us to do, that not T, i.e. the theory is falsified. Now, Popper himself admitted this logical derivation problem, as well as conceding that one may protect the core of a theory by instead modifying auxiliary assumptions in the theory rather than the theory itself. In fact, one may also modify different aspects of the theory, such as definitions, or extend the interpretation of the theory, etc. For Popper then, in order to save his falsification methodology, he claimed that this criterion of falsification is much broader than the deductive logical implications, as it serves as a broader methodology governing essentially how scientists should respond to scientific refutations, as demonstrated in experiments. What is, however, clear is that if we merely consider using falsification as a strict demarcation criterion between scientific and non-scientific theories, then as a result of the Duhem-Quine thesis, Popper's methods fails outright. Again, see the picture of the logical derivation. However, we should still explore if the modifications Popper made have an effect on diminishing the effect of scientific holism. Thus, as a broader methodology, falsification obviously has merits, such as requiring that a theory leave itself open to refutation. Any theory not doing so is considered unscientific. Also, as a consequence, Popper viewed scientific knowledge as never really reaching a final truth concerning knowledge, which closes the door to a strict true theory, no matter how many refutations a theory has passed via falsification. Thus, this introduces another scientific virtue as a consequence of his theories, namely that science is always tentative, where one can only corroborate a theory through its hypothesis passing a severe testing criteria. Note also here the strong relationship between corroboration and falsification if we follow Popper here, as precisely what it means for a theory to be corroborated is seen as a direct result of unsuccessful falsification attempts via strict testing. It's important here to highlight that strict testing as a high degree of corroboration requires risky, highly falsifiable tests according to Popper. Therefore, if a test is weak, it would mean that surviving it adds little corroboration according to Popper again. Lastly, it should be noted that Popper did not believe that we could ever tell whether a theory is absolutely true, but we could come closer and closer to the truth without reaching truth itself. This is made clear in the following video clip.
Human fallibility, human mistakes are made because one can sometimes give good reasons for a thing to be true and bad reasons for a thing to be true, but never conclusive reasons for a thing to be true. One cannot generally distinguish between truth and false by a criterion. This does not mean that we shouldn't try to find truth, and it does not mean that we shouldn't get nearer and nearer to the truth. It doesn't even mean that we cannot know that we have got nearer to the truth. We can know we have got nearer to the truth, but it means that we can never know that we have reached the truth.
Thus, one important feature of falsification is that while falsification does not tell us whether a theory is true, it can be used to rule out an ever-increasing amount of generalized theory plus auxiliary statements. We can argue that this line of practice or methodology is useful as for while it is the case that extra added assumptions protect the core of the theory, it is possible to construct strict tests which target these assumptions, whereby falsifying these assumptions forces a revision of the theory, and in this sense we are making scientific progress. We could again look back at our example of the black swan, for even if we discovered a black swan as a falsification, then adding auxiliary hypotheses such as the swan was not really black due to poor lighting, or the black swan wasn't a swan at all, etc., etc., then we could again test these new assumptions and make progress. I won't go any further here discussing responses aimed particularly at Popper. I will make a dedicated video though for sure in the future on falsification, where the former part of Popper will play an essential role, of course. Lastly then, let us briefly look at another response. We consider here a response given by the philosopher Adolf Grünbaum, the Duhemian argument from 1960. And for a fun trivia, he actually had Bas van Fraassen as a student, who we have mentioned earlier in earlier videos. I will, of course, link the article in the video in case anyone is interested as well. In any case, Grünbaum again accepts the logical consequence of the Duhem-Quine thesis that we have looked at earlier, where his disagreement lies with the further extension of the logical argument. Hence, if we start from the negation of the conjunction not H and AI in the end of our slide, then Grünbaum wants to deny the extension from this step. namely that we can always find non-trivial auxiliary assumptions such that we can preserve the hypothesis H by replacing our existing auxiliary assumption set AI with A prime I to obtain the conjunction H and HI prime, where we again may rewrite our implication to a predicted outcome or observation as the implication H and A1 prime etc. implies P. Now remember, from the Duhem-Quine thesis we have that it is impossible to decisively falsify H, since we can always make an adjustment elsewhere in the theoretical system that can always accommodate the observed evidence, which is exactly what we now have in our implication. But the objection from Grünbaum here will be that this strong notion of always has not been justified. That is, he claims that there is no purely logical theorem which guarantees that for every hypothesis H and every inconvenient observation P, there exists a scientifically acceptable non-trivial set of auxiliaries such that H and A prime I implies P. In reality, then, such an existence of a new element or set of auxiliary assumptions, A prime, must be shown to exist or constructed in each case, according to Grünbaum. The core of the argument is then that why are we so epistemically certain that such a new A prime will exist, if it is not strictly logically entailed or guaranteed strictly by the logic alone? To quote the man himself from the article with slightly different notation that we have used, we have the following extract. No general feature of the logic of falsifiability can assure for every isolated empirical hypothesis H, and independently of the domain of which it pertains, that H can always be preserved as an explanans of any empirical findings. O, whatever by some modification of the auxiliary assumptions A in conjunction with which H functions as an explanans. For Duhem cannot guarantee on any general logical grounds the deducibility of O from an explanans constituted by the conjunction of H and some revised non-trivial version R of A. The existence of the required set R of collateral assumption must be demonstrated for each particular case. Just for clarity here, explanandum is what we wish to explain and explanans is the explanation itself, if that was unclear. One response to this has been to trivially invent a new A prime, which we can choose as existing each time by choosing this variable equivalent to the observation or prediction P in each instance. But observe here that Grünbaum has excluded such trivial cases, so that doesn't work. Here in this brief last section or summary, I want to look at some of the consequences for the scientific methods themselves, or how the Duhem-Quine thesis poses a problem for the methodology of science. What we have seen throughout the video is that given some empirical body of evidence E, it's not immediately clear what scientific beliefs should be accepted and what should be discarded. Crucially, the thesis, as we have explored, does not let us test individual hypotheses H in isolation, but rather as a set of conjuncts from which the negation is again directly related to the conjuncts. This again posed an especially nefarious problem for Popper and his program of falsifiability, as we saw. We also looked at Quine and his extension of the thesis, which led to a rather radical methodology, where when empirical stringent test conflicts with his notion of a network of scientific beliefs, there may be considerable latitude concerning what should be revised. Crucially, Quine wants to go as far as to claim that even logic and mathematics could in principle be reconsidered. Of course, this reconsideration would come, as I have argued before, at a very high cost, where in the process it seems to me the boundary between mathematics, logic, and science could be eroded. Lastly, to end on a more positive note, we should observe here that we have only explored here throughout the video this scenario whereby modifying assumptions leads to a false or dying theory to remain longer in circulation. But we should also give consideration to the fact that it's possible to, by retaining the theory and modifying auxiliaries, to produce a major discovery, hence to iterate we are not guaranteed that this process results in the delay of the abandonment of a totally inadequate theory, where there is also creative, productive work to be done by re-evaluating assumptions. An example that immediately comes to mind is one that we have discussed in another video, namely the re-evaluation of the assumption that all of the planets significantly affecting Uranus were already known that led to the discovery of Neptune. The background here being when Uranus did not behave exactly as Newtonian mechanics had predicted that it would. Alright, so that finishes off this video. Please like, share, and subscribe, and I will put out more philosophy videos in the future, and I'll see you in the next video. So cheers!